Welcome back to our tea experiment. I've decided to call it the T cubed experiment because it includes 3 T's: time, the small t, temperature, the big T, and tea, which we've called old style tea. So we've got a T cubed experiment. This is hopefully my last video before we actually do the experiment. I've done another test as expected, and I've got some more information for you. So my test was reasonably successful. I got 4 groups of tea bags of 10 that weigh almost exactly the same as each other. I've got a beaker that contains 1,000 milliliters of distilled water that I've made, and it has space. And I've got a way of dipping 10 tea bags in all at the same time, which is to attach them to a round piece of metal and dip them all in at the same time on a stand, trying to get that in front of you. That is all functional. Of course, some new problems arose. Firstly, it's difficult to reproducibly get the same rotation and reproducibly get a good temperature, so a constant temperature, using the setup that I had. So I'm going to have to go to a better stirrer setup. Luckily, we've got one of those. So I've got a better stirrer heater, and I might put some insulation around the beaker, but I don't want to. I've produced a dip machine, which is effectively a bar of stainless steel, a little bit of stainless steel with a little cup on the end, and I tested that. That works pretty well. You can dip it in. There is a problem. There is an error on T for time of a little bit, because when you dip it in, it goes in, but it's very difficult to concentrate on dipping it in and the time at the same time. But that's okay, because we're filming it. So we will not get exact numbers, and that is extremely common in science. So extremely common in science. We would like to have data points every 15 seconds or every 30 seconds or something, but they're actually after 14 seconds, after 32 seconds, and then whatever. So they don't quite match up. And that's all right, as long as we know what they are. Just the same as the mass of our tea would be nice if it was a round number, but as long as they are very close to each other, it doesn't matter what they actually are. If they varied by more, we would have to vary the volume of our container, the volume of water that we used, to counteract the fact that we're using different amounts of tea. So the new thing that I discovered was when I boiled the water, my thermometer, the new thermometer that I was using, also doesn't read 100 degrees. So backtracking, the old thermometer that I was using was an alcohol thermometer. Those are known to be not very good, and that read 95 degrees and the water appeared to be boiling. I decided to check my other thermometer, which is a mercury thermometer. Those are typically better, but that doesn't read 100 degrees either. It reads 103. So therefore we are going to have to set it. Mercury thermometers are very linear within the range of boiling and freezing water. So all we need to do is measure the freezing point of water and the boiling point of water, ideally distilled water, and then set that as our 0 to 100 range, and we can then fix our temperature afterwards. Because the temperature of boiling water is very close to 100 degrees centigrade, particularly because in Cleaver we are almost at sea level, which means that it's almost the exact definition of 100 degrees, so we're okay. If we were at a different altitude, then we would have a problem, but we're not. And the temperature of boiling water is only affected by air pressure, so it is mostly affected by altitude. So there we are, reasonably safe. We will not be accurate to less than a tenth of a degree, but I cannot guesstimate a reading off a normal thermometer to less than a quarter of a degree anyway. 0.2 maybe. Okay, so this is our experiment. Extract dip samples of about 1.6 milliliters from a liter of tea, containing 10 tea bags of about the same mass. So 10 tea bags together weighing a standard amount, about 18.73 grams, I think they are. So I've already grouped them into 4 groups, and I had to throw out a whole lot to make that work. There were 50 in the box, and I'd already used some, so there was no way I was going to get 5, but I would never get 5 anyway because of the way you have to choose the samples. It would have taken me ages otherwise. I've chosen 1.6 milliliters for practical purposes because that gives me 1 milliliter to measure the brownness and some samples to measure the amount of caffeine. So that's our temperature T, which we will vary at times: 15 seconds, 30 seconds, 45 seconds, 60 seconds, 90 seconds, 120 seconds, probably none in between, 180, 240, 420 and 600, so 10 measurements, which means that we get a 1.6% error on the last measurement from the volume, which is okay. So we should expect that. We're going to stir it and we're going to try to heat it to keep the temperature constant. So to measure the caffeine from that, we will have to extract the caffeine from a 200 microliter portion. That's to make it not overdo our measurement. Using a milliliter of carbon, so dichloromethane, CH2Cl2, which is very good for extracting it. And I forgot to mention the base solution. Possibly at the beginning of the measurement, when caffeine is low, we will have to do a little bit more than that, but we have plenty of sample. Then measure this using a standard curve. So I have to make a standard curve at 275 nanometers using the same spectrometer, using the same extraction method and the same amounts, but using caffeine that I have as pure sample. It's not 100% pure, so we have to allow for the fact that it is not 100% caffeine. It's 98 point something percent, and that will obviously shift this curve slightly. Then we can say exactly how much caffeine we have. If we don't do that, we can say how quickly it comes out anyway, but if we do this, we can then actually have numbers on our graph, which is way better. It's way better to have numbers on your graph if you can. It's not necessary, but it is always better if it's possible. So we're then going to try to measure the brownness, which would be taking the whole solution, but in a short path cell, because it's too dark for the big cells. Also, it means we don't need so much solution. We can measure that between the range of 500 and 550 nanometers, because there the signal, or the ratio of the signals, is about flat, but the signal is quite steeply curved. So we're going to use a normalized average, which will be the measurement at point T, the time that we choose, the time point we choose, which will be different values, and the measurement at T infinity, which will be the longest time that we take. And then we're going to normalize it by dividing the time, the measurement at this time, divided by the T infinity. So in this case, it's 0.51, 0.5, 0.8, and 0.25, 0.5. So it's going down between 500 and 550. I've only given 3 points, but there's a lot of points in our measurement because it measures every it measures quite a lot of points anyway. I'll have to look up how many it measures. It depends on the exact settings, but we get a lot of points. We can divide them by each other in a computer, and then we can take the average. So in this case, we get 0.5 from this 0.5 and 1, we get 0.5 from 0.25 and 0.5, and we get 0.625 from this one. Taking the average, we'd have to add them all together and divide by 3, which would give us some value of about 0.55 or something, 0.58. That would be our value for brownness. The advantage of doing that is we've generated less randomness by using more data that we will have anyway. So although we don't have more points because we haven't taken more than one sample, we can have more points at different wavelengths, which reduce the error, but we need to be aware that they reduce it in a specific way, because obviously if my light source changes brightness during the experiment, it will reduce them all. So that is a bad thing. But if we get a spike in our measurement, so a piece of dirt comes flying through, that will not affect our measurement very much because it will be removed in the averaging here, or it will be reduced massively in the averaging, and the probability that we get a spike in each measurement is higher by the amount of points that we average over. And that will mean that we get a comparatively smooth result. As you saw in the test version, it was kind of a wobbly curve, and I've taken a bit where it's reasonably straight and flat so that we can get a good measurement of the brownness. This is not, unlike the caffeine measurement, it's not a number that we can use for anything because it's normalized to T infinity. So it doesn't have standard values. We can say how much absorption there is at that wavelength. We can do that. We can publish that as well. Or we can publish our T infinity values. But our brownness ratio, which will be going up over time as well, will not be standard between different measurements unless we decide to do so. So we can decide whether to do it inside the measurement or inside the set of measurements, which will mean that the hottest one for the longest time will be the brownness probably. But we'll get a value for T infinity average, and we'll get a value for T. The reason that I've chosen this is because, the reason I've chosen this method for doing it is that I noticed while doing the test experiments that the variation in temperature was the thing that I had the least control over. So more volume and less experiments means that the variation in temperature will be lower. So it will be changing over the experiment, but it won't change very much, and it will be a value, but it won't be the value necessarily that we aimed at. So if I want to measure, if we decide we would like to measure at 95 degrees, it won't be 95 degrees, it'll be a different temperature. That is what is a very common factor, and in this case it means it's almost impossible to do a set of measurements in different beakers because we will never hit the same temperature twice. It is possible with more controlled systems. I do have a way of doing it, but not at these temperatures, unfortunately. So we have a temperature controller that will control to 0.1 degrees, so you can get out temperatures like that. But near 100 degrees in water, it doesn't like it because water absorbs a lot of heat to evaporate, and that will cause a problem. I also have to note that to keep the volume constant, because it'll take a while to get to a constant temperature, we will have to make a mark on our container and see whether a significant amount is lost. So we will also need to do that. Okay, so next time I will probably manage to do the experiment. Then we will see how quickly caffeine comes out of tea. Then we'll have to deal with the results, but that will be your job. And then I need you to write a paper about it.